I think we can all agree this was something special. We'll do it again. I think next year we'll probably try to do it at Stanford, as again a joint effort with PI. And I think we'll do it for a certain number of years until we either solve the problem or until I turn 75, in which case that will be here and they will make a big party for me, right? Good. Okay. I don't think these series of conferences should go on for more than 5 years, but 5 years sounds like the right time scale for cracking this problem, frankly, or at least making some major progress. In any case, Simeon's talk was very helpful for me to get started. This is not a joke. I'm too tired and too exhausted from this whole conference to try to compete with Simeon's, well, what should we call it? His immature humor. So instead, I will just use some of his remarks to illustrate a point. I originally, when I first talked at the beginning of the conference, I suggested a division into things that we can call the approximate but useful and the exact but useless, well, maybe not completely useless, and that holographic theories, good holographic theories, exact holographic theories, are usually too hard to do anything with, at least to do the usual simple things that we try to do, whereas approximate theories, things of the form, low energy or effective field theory and things can be very, very effective, very, very useful, but they're not exact, and they don't keep track of counting, and they don't keep track of degrees of freedom with the same precision. So I think, in some sense, what Simeon said today was an illustration of that I think it'd be fair to say that the SCFT, at least at the present, seems to belong to the realm of the approximate but useful. Or useless. Maybe approximate but useful. No, let's not. No, that's right. That's right. Look, Juan used it very effectively to talk about three-point functions in ordinary inflation. Never mind. Okay. What I want to talk about is the possibility of a more exact theory, and in particular, the exact theory would be, as Simeon suggested, the theory as seen from the point of view of an observer who you said lives forever, or an eternal observer. I would say a little bit differently, who gets to look back and see an infinite number of degrees of freedom, as opposed to observers in de Sitter space, and possibly exact FRW CFT, but I'm not going to be talking about FRW CFT so much as just what goes on inside a hat and how does it refer to the rest of the multiverse. And in particular, I'm going to ask the question, can any of those ideas help illuminate the measure problem, specifically the measure problem? I'm going to formulate the measure problem. Again, this is something I talked about the first day that I was here. I'm going to formulate the measure problem in an extremely simple way. I'm not going to go through what I told you last time, but I'm just going to remind you very quickly that one way of thinking about the measure problem is to, well, in talking about the measure problem, I will subscribe to the view that the measure problem is basically a problem of cutting off the multiverse at late times, and it's basically a problem of correctly drawing green lines being the cutoff lines. And I gave you some examples where we don't have any green chalk. So do we have? No, maybe we do. Yeah, we actually do. Okay. Here's the green line, the cutoff line. Everything below the line is counted. Everything above the line is not counted. And we talked a little bit about what happens if a bubble nucleates in this geometry. And I made a very simple picture of a bubble, just a square bubble. And I said, well, we have to have a rule for what happens to the cutoff surface. If we take the vertical axis here to be proper time, and we just draw the green line right through the bubble, then we would define what we would call a proper time cutoff, and that leads to major disasters, major phenomenological disasters, and so that can't be the right rule. And I gave you a family of rules based on what I call Douglas's principle or Douglas's rule, Douglas Stanford, that you shift the cutoff surface, according to a rule of conserving something. I call that something Q, meaning to say that whatever Q you excise when you put the bubble in, the missing Q here should be made up for by the amount of Q that you put back. And I gave you some examples of what Q could be. Q could be volume, but then of course I would have to specify, am I talking about volume in string units? Am I talking about volume in some other units? Or it could be number of horizon volumes that gave a different measure, or it could be the amount of information, which I'll talk about a little more as I go ahead. But I gave you some different examples of Qs, but all of them had the nice feature, and it's the feature that really strikes me. It strikes me personally as possibly very significant, that they all led to an answer for the measure, in particular for the measure of the cosmological constant, which had this e that Ben talked about, that I talked about, e to the minus h times the time scale at which observations occur, times prefactors 1 over h to various powers, those prefactors depended on what you chose as, for Q. That was a pattern, nice pattern, that may be significant. I mean, when people sit around and say, oh, the measure problem, nobody ever makes any progress on it, it may not be true. This may actually be, this is a 3 here, excuse me. You can catch me. And of course, the significance of this is it tells you that whatever h is, h being the Hubble constant in the bubble of interest, that the measure tends to suggest that the scale of the Hubble constant and the scale of observations are pretty much similar. I would love to be able to derive this from something deeper. The problem is, sure, we can make up rules like this, and some rules look better than other rules, and maybe some rules look really, really interesting, but we're missing a set of principles which would tell us, for example, to use these Q rules and not to use the proper time rules, and you can get things which are worse than the proper time rules. And so I would love to derive this from something deeper, from something more fundamental. And I'm going to talk about, what I'm going to talk about is so poorly, what shall I say, confirmed by mathematics that I have barely no equations at all, just some pictures. I'm just going to show you what I'm thinking about, how you might derive it. Yeah. I didn't say anything yet. How could you ask a question already? I did write an equation, yes. Okay. The origin of time. 0. Yeah, I don't know. Don't worry about it. It's not important. No, what's important, okay, good. What is important is that if there is an initial condition on eternal inflation, we're talking about eternal inflation, if there is an initial condition on eternal inflation, we want to be very late compared to that, but it doesn't matter how late. If we get late enough, hopefully eternal inflation, yeah, the initial condition. Okay. So because they are supersymmetric, hats, the bubbles with 0 cosmological constant, have a particularly good chance of having some exactness to them. Because the observers who live in them can exist eternally and look back and see an infinite amount of information, an infinite amount of entropy, perhaps they have the best chance of having an exactness to the statements that can be made. And that's the framework I'm going to think about, although I'm not going to be talking very much about FRW CFT. I'm going to be talking about observations that could be made from within the hat. Okay, one question, a central question for what I'm going to be talking about, is whether there's a complementarity, in the same sense as black hole complementarity, between the degrees of freedom of a hat geometry and those of the rest of the multiverse. Not a complementarity between the degrees of freedom of a hat and, or the degrees of freedom on the boundary of the hat, the rim of the hat as some people call it, but rather, and the FRW geometry, but a complementarity between observations that can be made within the FRW geometry and the rest of the multiverse. And equally important is the dictionary between the observations that can be made inside the FRW region and the rest of the multiverse. Is it simple enough for us to be able to use? In other words, does it violate the rule that holographic descriptions are so impossibly scrambled that we can't learn anything from them? And, of course, I don't know the answer, but I'm going to guess. All right, this just is the iconic hat, the hat geometry. It's a bubble nucleated inside a false vacuum. You all understand it. This is the Penrose type diagram for it. Spatial slices consist of hyperbolic planes. Hyperbolic planes are Escher disks, if you like, or three-dimensional Escher disks. And we can imagine a census taker or an observer at late time looking back, and that late time observer looks back and sees photons and other junk, and can count how many degrees of freedom does it take to describe his observations. And if he looks back, and if you use Busso bounds and you use just covariant entropy bounds and so forth, as the census taker gets later and later and looks back, he sees a larger and larger area on his backward light sheet. That area eventually diverges, and so that's a statement that to describe all of the observations of the census taker would take an infinite entropy, or an infinite amount of information available. So S max for the census taker is infinite. Okay, now that leads to a very interesting, I don't know whether to call it a paradox. It's not a paradox, although I could state it so it sounds like a paradox. Let me try to state it so it sounds like a paradox. I've purposefully drawn the hat up here as being tiny, as if the geometry nucleated at a very late time. Then the whole thing up here looks hardly different than just a point in the future of de Sitter space. Practically looks like a point in the future of de Sitter space. To make the point even more, I would push this up even more, make it tinier and tinier until you could barely see it, and then it would just look this horizon. This would be the horizon of the census taker. Looks pretty much indistinguishable from the horizon of the de Sitter space. But something's funny. In that almost limit, the number of degrees of freedom in the hat to take observations in the hat is infinite, but the number of degrees of freedom in the de Sitter space for a de Sitter observer at this point in the causal patch of the de Sitter space is finite, and it's just S de Sitter. Question: what does all of the rest of the information carried by all the other photons, by the infinite number of photons that eventually become available to the census taker, what do they mean? What information are they carrying? There's no more information in the backward light cone of the de Sitter space than S de Sitter, but the presence of this little bubble here suddenly generates an infinite amount of new information available to the census taker. My hypothesis is that really what it has to do with, by a complementarity of some kind, is the rest of the multiverse. In other words, the first S photons that you see tell you nothing more than what you could have gained by looking back into the backward light cone of the de Sitter space. It's the ones after that which have some new kind of information, which the only thing I can think of, and what I want to believe, is that it has to do with the rest of the multiverse. So let's talk about complementarity a little bit. Yeah, okay, that's just Raphael's drawing. Let's talk about complementarity very, very briefly. Here's and let's start in the black hole context just to make the point. in a black hole, the point A is behind the horizon. Let's imagine that there's some observable A that we're interested in, and it corresponds to observations that could be made behind the horizon by an infalling observer who at every point is in a frame of reference, his own frame of reference, which everything that takes place is low energy. An infalling guy carrying his laboratory with him, doing experiments, and there's some observable A that can be described in strictly low energy terms in the infalling coordinates. Right? So A could stand for any kind of things. It could stand for a field operator over here. It could stand for a whole algebra of field operators associated with some region of space-time. Whatever it is, think about it. The question is there necessarily, does there exist an operator in the outgoing Hawking radiation here, which I haven't drawn, does there exist an operator composed out of the outgoing Hawking photons, which in some sense is a direct reflection of an image of A, let's call it. And all I will mean by it, the only thing I will mean by it, I'm never going to say that measuring this other operator effectively tells you what happened behind the horizon. There's no way to confirm that. All I'm going to mean by it is that mathematically, whatever this other operator is, it has exactly the same probability distribution when measured outside by an outside observer as the operator A had in an infalling frame. Okay, is there such an operator, and how do we construct it? So here's what we do. It's very simple. It's a couple of lines, and I don't even need equations for it. You take A, and in the infalling frame, where everything is low energy, you just rewrite it in terms of data on initial backward light cone here. That's just another way of saying you solve the equations of motion backward, and you rewrite A in terms of data on the backward light cone. Mathematically, the object on the backward light cone here that reflects A would just be some unitary conjugation of A, conjugated by the low energy unitary time development that would take you back to the light cone here. Can you always do this? I don't see any reason why you can't do this. Remember, it's all taking place in a completely low energy reference frame. No high energy physics involved in it at all. Then, once you've done that, you take the operator that you've expressed it in terms of, and you run it forward in the same way, but not with the time development in the infalling frame, but with the time development in the frame that stays outside the black hole. That means the S matrix. That's the big scrambler. That's where the bad stuff happens. That's where the information that A might be carrying is completely scrambled up among the degrees of freedom of the Hawking radiation. But if that picture is right, then the operator up there, let's call it A bar, is just a unitary conjugation run backward with the low energy operator, run forward with the S matrix, and it would suggest that there's some operator in the Hilbert space of the outgoing things here which has exactly the same probability distribution. Now, the reason I'm interested, yes? Yes, that's right. That's right. Exactly so. The reason I'm only interested in probabilities, the only reason I'm only interested in the question, does this operator have the same probability as this, is because I'm interested in the measure. I just want to know, is there a way from outside the horizon of finding something that has the same probability distribution as A? And it's made up out of the Hawking photon. So I believe for black holes, I think we're pretty sure this is right. Okay, now let me come to the hat geometry. Now I've focused in, let me go back. Damn it. There it is. I'm going to focus in on this corner over here, only for convenience. Just because I can write down the metric nicely. In other words, I'm going to blow up that point and study what's going on very close to here. I don't have to do that. It's just all sorts of equations get very simple if I do. All right, so there's that point. And I think, who was it, Daniel? Daniel, somebody labeled the three, Daniel labeled the three different regions of interest. Here's the FRW region where the census taker lives, that's region 1. Here's region 3, that's the rest of the multiverse, that's what we're interested in. And here's region 2 that happens to be a warped compactification of 2 plus 1 dimensional de Sitter space, warped on a line interval with some funny kind of properties, but that's all right, though. I'm not going to use that very much today. Let's put some coordinates. I've blown up this point, so the direction's perpendicular. In other words, the 2-sphere, I'm now just going to replace by the tangent plane. So they'll have coordinates called x, which are just Cartesian coordinates coming out. And then I'll use 2 light cone coordinates, which come out of here, u minus and u plus. And I'm just going to tell you now what the metric of this thing looks like for a Coleman-DeLucia bubble. For a Coleman-DeLucia bubble where you focus in on this point over here. All right, it turns out the symmetries of the Coleman-DeLucia bubble completely dictate pretty much what the form looks like. And it looks like a function of u plus over u minus. In other words, a thing which has scales, doesn't scale with u plus over u minus, divided by u plus squared times du plus du minus plus dx dx. All right, so can you see anything in this? First of all, down here in the de Sitter region, f happens to be this thing over here. U plus u minus is just the u going in this direction here. And all this reads is du plus du minus plus dxi divided by, let's call it u naught squared. That's a familiar form of de Sitter space in conformal coordinates. Okay? Out over here, f goes to 1. Out over here, f goes to 1. And this is the general form. I could give you specific forms for thin wall approximations and so forth. But this is a fairly general form. And the only thing important about it now is that it has a scaling symmetry. The top here is a function only of u plus over u minus, and the u plus over the u minus divided by u squared. Everything scales by rescaling the coordinates by a factor of lambda, let's say. If I rescale the coordinates, this is scale invariant. That's the remnant symmetry of the Coleman-DeLucia instanton when you focus in on this point here, and it's a kind of scaling symmetry which scales you toward or away from this point 0 over here. Scales you away from it or toward it. And that's the geometry. That's the whole geometry that I'm going to look at, that I'm going to think about. Question? Yeah. This one here? Yeah, that's this one. That one. That's the future light cone of. Yeah. Yeah, that's light like infinity. Say it again. Wait, say it again. Did I write something wrong? I may have written something wrong. No, it's actually, no, it's 1. Yeah. Yeah. Okay, but it is not important. It is not important. The only important thing is that it scales. And, what's that? The bracket is, I'll have to show you. This surprises me every time I derive it, and there's some funny coordinates but I can show you what it is, but it's not important. I'll tell you. This is the vicinity of a point. Yeah. It's actually the x coordinates are actually a sphere. That's the tangent plane perpendicular to some direction. No. Okay. All right. So now what's the question? The question is if there's some observable here, an observable could have to do with some fellow living in de Sitter space, or it could have to do with the question of whether a bubble nucleated over here, or it could have to do with the question of how many observers are inside such a bubble. All the kind of questions we would love to be able to ask and answer about the rest of the multiverse. And now the hypothesis that now I cannot support this by any equations, It just goes back to this question, what is the extra information, the extra amount of information that's in the large amount of Hawking radiation? In other words, the extra amount of information that's there if you gather and look at more than S photons. If you look at 2S photons or 3S photons or 4S photons, correlation functions among them are containing more information than should be in visible coming in through the de Sitter region over here. And so it must be something else, guessing that the something else is this. All right, so I want to play the same game, assume that A can be pulled back using the low energy equations of motion and then run forward, and the running forward will scramble it extremely much. Yeah. Okay. We're focused. That's right. Some gets pulled back to the right. But you know, it's kind of like light. If I am focused in near the corner here, then it's kind of like light cone coordinates. The one direction that that doesn't pass through the surface here is a set of measure 0. Yeah, right. Okay, that's right. So let's say we're very close to that tip. But this little region over here should have everything in it. It should have the full multiverse in it. So we should be able to answer everything we're interested in by looking close to there. Yeah. So that's the logic, right? Say it again. It doesn't matter that A is also equal to well, I'm saying that even stuff coming in from the right will pass through this cone here, unless it's along a set of measure 0 in this limit. We can do a little bit better, but let's just leave it at that and not the. All right. Now, what's the idea of the new kind of hat cutoff? Let's call it a hat cutoff. Again, it's a green line, but the idea of the green line is going to go something like this. Question: we want to introduce a cutoff procedure for the multiverse. We're going to do it by introducing the census taker's cutoff. The census taker's cutoff is just as census taker time goes forward, he looks back. First he looks back along this green line, then he looks back along that green line. Later he'll look back further green line, and he'll detect more and more photons. I'm going to assume that the photons that carry the message A, whatever those photons are, I'm going to assume that they come in a sort of package, that they're packaged in a manner that there exists a last photon. This doesn't have to be a completely exact concept, but that there exists qualitatively a last photon that's necessary in order to decode whatever A is. If I can find for A what the last photon is, then I will say that A falls before the cutoff if the message can be gotten out before this green line, and it is later than the cutoff if the message is later than the green line. Now, this may allow me to redraw green lines in here that represent the same green lines in here. If here we draw a green line, and now we look at all the A's which reflect into something which can be seen before the green line here, that's something which should exist before the green line extrapolate, or the dual or the complementary green line behind here. So that's the idea, to try to make a geographic mapping between what's happening out here and where these packages of photons occur for a given thing. All right, what do we know? Well, first of all, we know on the scaling, what I'm going to draw here, this is not a domain wall. The domain wall would be over here somewhere. Incidentally, domain walls and all the hyperboloids that describe the different de Sitter spaces in here would just be straight lines in this geometry. The scaling symmetry is the symmetry. They would all be straight lines. I'm going to draw here a stretched horizon. This is the horizon of the census taker. I'm going to draw a stretched horizon. It's mostly just useful for drawing pictures. But I will pretend that this stretched horizon here has the usual, well, we'll see what it does. I'm going to assume it behaves like a mirror, but we'll come back to that. Okay, so, right. Now, another thing that I didn't quite draw on here, may come up in other drawings, is that the information associated with A, the information that's associated with A can be thought of as a kind of incoming signal. I drew it coming in along light cones here, but of course some of it also comes in from other directions. I think there's a reasonable argument to be made that the bulk of it comes in along from this direction here, but I'm not too sure of that. I'm not completely sure of that. All right, but here's a message is coming in here. That message is just the running backward of what A is, and then running it forward back into here. So a message comes in here, and that message produces a bit. A bit comes in, and that bit gets emitted back into the Hawking radiation. And I've just drawn that. And I've kind of drawn this as if it's a mirror. Bit comes in and gets reflected off here. That's the picture I want you to keep in your mind. The one thing that I know is from the scaling symmetry that if the last photon associated with A over here comes out over here, then the last photon associated with a rescaled version of A comes out at a rescaled time, at a rescaled U. So that's one piece of information that I have about this map. Here's the mirror right here. No, yes. We're going backward in time. What we're doing is saying whatever A is, it can be rewritten in terms of operators in the past. And in that sense, you can think of A as a message from the past by solving the equations of motion backward and then saying A is some function of the things that were in the past here. So in that sense, A is, we can think of it as a message coming in here. Once we think of it as a message coming in, we can think that that message is reflected. Now, that's the idea. That's what complementarity is. Right, that's what complementarity is. That there's a version of it over here, and there's a version of it over here. The reason, why don't I just work with this? Why do I have to go to such a complicated story and work with this? The reason is because nobody has told me yet from this side how to define a measure in a unique way. Here I'm suggesting that the cutoff procedure is the cutoff procedure that the census taker would use. And since it's all right, so let's get rid of the second guy over here and redraw this picture. A message comes in from the past, and one version of it gets reflected off this way. The other version of it is what the observer in here sees. You can worry, is this quantum cloning? No, of course not. There's no way that an observer over here can collect this message and get back over to here and see quantum cloning. So this is not going to be a problem. It's a similar argument to the black hole argument. Okay. Now I'm going to make one more assumption. I doubt that this is the last assumption that I've made. All right. Looking at A over here, and what I actually have in mind is that A is about horizon size over here. If this is the de Sitter region, that it's about horizon size. You can see not the last photon that comes out, but you can sort of see the last light ray going in. Here's the sort of the end, the late end of the message that comes in that creates A. You can just think of it as A being created by bits which flow in from the past, and here's that last bit that was coding the information in A here. And what I'm going to assume is that there's a delay between the time that the last bit comes out over here, the last bit comes in, excuse me, and the time that the last bit goes out, that the package of information over here is terminated. The question is, how much time will I assume along this stretched horizon elapses between the time that the last bit comes in that codes A and the last bit goes out. And now I'm going to use something which may or may not have justification, but it's something which comes from black hole physics, and it comes from papers that I learned from Patrick and John, Hayden and Preskill. It's black holes as mirrors, the paper Black Holes as Mirrors. Now, what's important in the paper Black Holes as Mirrors is that there was a lot of radiation emitted before the stuff that went in, but there is, of course. There's all this radiation that was emitted into the hat in the past, and so most of it's there. So in Patrick's language, I suppose this is entanglement-assisted message sending or something? What do you call it? Something like that, right? All right, and under those circumstances, maybe even more broadly than those circumstances, the time delay for a message to come back out is proportional to the number of bits, or let's say if this is a horizon size system over here, and what we're trying to do is not just decode some particular thing, but all the information that could be in A, the number of bits in A, or the number of bits coded by some collection of operators here, let's call that SA. We can also think of that as the number of bits coming in, that the time delay is of order SA. Okay? So now I know something. If I can tell you what the entropy of A is, then I can tell you where the last bit comes out. I've managed to make my mapping. Okay. Now, there's two kinds of entropy of A. One kind of entropy is just the intrinsic entropy of A. It would be the same if A was over here or if A was over here. It would be bigger, of course, over here just by the telescoping of this conformal squeezing. If A was over here, an intrinsic entropy of A, which if A corresponded to the full information that could be obtained from a horizon here, it would just be the de Sitter entropy of what's going on in here. The other kind of information that's stored in A has to do with location. It has to do with location. And what I'm going to take it to be is a entropy of location along here. There's information in knowing where it came in, and it's locational entropy or positional entropy. Now, how this works is the following. If you push this A up, this little region, let's see, I think I actually have it. Is that where it is? No. Yeah. Think about this message occupying a certain distance along here, along the U-axis, or along one of the, along this U-plane here. It has a certain delta, which is measured in the same units as U is measured. How big is that delta? And the answer is the higher up toward the top, in other words, the smaller U naught here, the smaller this red line is, and therefore the smaller delta is. If I push this way up to the top here, then delta gets very small. And what happens when delta gets very small? The number of places you can stick it in on the U-axis here increases. Basically, we should expect that the positional entropy scales like inverse of log of delta. The number of places that I can put this in scales like the log of the inverse of delta. The smaller delta, the more information there is in where this came in. This is incidentally familiar from black hole physics to some people who have thought about similar things. So it should be a log of 1 over delta, but it's got to be measured in units, which are the scaling units. This should be scale invariant in the scaling here. And that means it should be measured in units of U minus, where U minus is just the U minus where this came in. Another way of saying it is if U minus here happened to be 1, then the positional entropy would just be 1 over delta. All right, so the positional entropy is just log of U naught over U minus. Now, next, the time delay along here, from the time that the message came in until it's fully emitted, is assumed to be proportional to the total number of bits carried by this message here. And there are two kinds of entropy, two kinds of information, positional entropy, SP, and intrinsic entropy, SA. If you put those pieces together, that the time delay is given by one thing, and you use the positional entropy that I wrote down before, I'm not sure where it is, the positional entropy involved the log of this ratio here, and you use the fact that U's are exponentials of time, they're exponentials of ordinary time, then you find that the last photon comes out at a time that scales like U naught, the U naught of this point over here, times e to the minus the entropy of the intrinsic entropy. Now this is kind of interesting. First of all, it says the more intrinsic entropy that there is, the longer it takes for the signal to come out. Okay. It also says that the further up here, the longer it takes to come out. But notice that the last photon to come out, its location is only dependent on U naught, on the time here. That has an implication for the way you extend the green lines from here into here, or the way the green lines in here are reflected in green lines in here. Green lines meaning cutoff lines. Okay, what it says is that the green lines in here associated with a given time simply become horizontal lines in here. They only depended on U naught. Now this can be changed. I did cheat a little bit in assuming this. There's more freedom than I've written down. You can get formulas where these lines curve, but it really doesn't change the logic very much. So I'm just going to leave it that way, that these green lines are horizontal lines. And what it says is that all the data which comes out later than this green line corresponds to data in here that comes out later than this green line. So we've mapped the cutoff. Without being able to even begin to decode any Hawking radiation, we've mapped the census taker's cutoff into a cutoff in here. Say it again? I don't think it's completely, I doubt that it's completely unambiguous. How big is the census taker? I think it's a very fair question whether how ambiguous it is. But yeah, I think it's the backward light cone of the census taker. So I think it's pretty unambiguous, yeah. To this line? It scales. It just scales. It just moves up toward here, right? It just scales. Right. There's a covariance under moving around the census taker that I didn't want to get into, and but I think as long as you're out near this corner, it doesn't matter. Okay, now what we're really interested in is what happens if there's another bubble nucleated. Where does the green line, if the green line was horizontal over here, where does the green line go inside the bubble? If we knew how to do that, we would be able to answer the question, which of these different rules to adopt. This one or this one? This one. Yeah. Yes, I'm using the idea of a stretched horizon and the idea that black holes or horizons are mirrors. What's that? No, the scaling won't change. The scaling won't change. The scaling won't change. Some numerical constant might change, but the scaling doesn't change. All right, so let me suppose now that this green line is the extension of some green line and try to find out where what it's an extension of. So there's a green line in here. I don't know exactly what it looks like. And I want to match it onto some green line out here. And in that way, instead of asking the question, what does a green line out here, how does it get bumped up? I'm going to say, supposing there was a green line up here, how does it get bumped down? But they're, of course, equivalent questions. Okay, so now take one horizon in here. One horizon in here. Here's that horizon region. And take everything in its backward-like cone. And I don't necessarily mean that everything is coming in from here. We could spread it out. But take everything from here. And let's try to ask, well, let's ask where its last photon comes from. No, let's not ask where its last photon. Let's be cleverer than that. I'll show you. We don't really need to know. All we know is that there's some intrinsic entropy of this, and the delta of it has a certain size. Therefore, the positional entropy has a certain size. The entropy, the intrinsic entropy, is the de Sitter entropy of this daughter bubble, and the positional entropy is just a logarithm of the size of this image coming down here. Now, for a moment, imagine that the bubble wasn't there. Just imagine that the bubble wasn't there, and instead, let's consider a family of small regions which have exactly the same delta, in other words, exactly the same positional entropy, but correspond to different height here. Correspond to different height. And let's adjust, let's push this up and down until we find a point where the entropy of this, were there no bubble, is the same as the entropy of this in the bubble. The claim is that the last message from here would have come out at about the same time as the last message from here. The reason is the intrinsic entropy of this is the same as the intrinsic entropy of this, and the positional entropy is the same. Okay. So, so how do I extend my green line? Once I find this height here, where the intrinsic entropy of this is the same as the intrinsic entropy of that, then I'm finished. Then I know where the green line should be. Same place, same height. Okay, now there's, of course, a lot of guessing, and I'm not sure that it's all true in detail, but I want you to get the flavor of an idea. Okay, so that would complete the green line, and in effect, it would tell me how the green line gets bumped up as I go from here. How does it get bumped up? Well, let's see what I have coming next. I'm not even sure what I have coming next. Okay. How does it get bumped up? It gets bumped up in a way that the entropy of this is the same as the entropy of this. Now, moreover, I could slice this green line here into lots of little horizons, size regions, and run them all backward in the same way. What would be my conclusion? My conclusion is that this green line would be such that the entropy excised out of here would be the same as the entropy excised out of here. That's what it would come to, that the green line that corresponds to a given green line of the census taker would correspond to a green line over here, which conserves entropy, entropy from one surface to another. Now, one problem. What on earth do I mean by the intrinsic entropy of this? And I'll tell you now why it's a problem. The entropy of this over here is typically much bigger than the entropy of a horizon of the parent de Sitter space. Why? Because this is the horizon of a de Sitter space with a smaller cosmological constant. So this region over here is bound to be many horizon sizes, correspond to many horizon sizes of the original de Sitter space. So what do I know about the intrinsic entropy of many horizon sizes of a region which is more than one horizon size? And here is where I'll have to make yet another assumption. My assumption will be that the intrinsic entropy of a region is essentially the best Busso bound, the tightest Busso bound that I can make for that region. Now, I say I'm assuming that it's the tightest Busso bound that I can make. If you can make a tighter Busso bound, then you will have yet another estimate for the entropy. This entropy should be less than the sum of all entropies associated with light cones or light sheets drawn in this manner here. But exactly how should I draw them? Should I draw this up at the top here? Should I put it down low? The idea that the entropy of the whole thing is less than the entropy of the sum of the parts, and each one of these horizon regions here, or one of these smaller than horizon regions here, has a certain entropy, that's okay. But how do I find the best bound? You find the best bound by moving around these points until you've made this as small as possible. I'll tell you what the result is. The result is incredibly simple. It just says that the best bound is gotten by dividing the region into horizon size and adding up the entropy of all the horizon size regions. What does that correspond to? It corresponds to the volume divided by the horizon size volume. That's the number of horizon size volumes times the entropy of one horizon size. And that's just the volume times the Hubble constant in the de Sitter space. The upshot. The upshot is that the rule for the green line is to conserve from here to here, not volume, but volume times Hubble constant, this information bound that I talked about. In other words, Q is not equal to volume, but it's equal to volume times Hubble constant, which is the number of bits, or it's the sum of the areas of these horizon size regions. It's the sum of the area of the horizon size regions. So that's a whole bunch of assumptions, very few of which I can honestly support, but it does give some kind of picture of where I want to go with this, where I want to go with it, and to derive some very coarse ideas about cutoffs. All right, so anyway, this is a special case, as I said, of a class of cutoffs. Depending on your choice of this Q, the argument that I gave you tends to suggest that Q is equal to entropy bound. But, for example, there are various bounds that you could concoct in this way, would include the scale factor cutoff. That would be saying that you conserve volume. That does not seem to be what this argument that I've given says. There's a light cone time cutoff. That's volume times h cubed is conserved. And there's this information cutoff. And I think that is what, well, that's what the argument tends to suggest, the information cutoff. Yeah. Volume is scale factor cubed. Right, volume is scale factor cubed. The reason I'm not so fond of volume, as I said, because volume you have to pick a particular metric. Now you could pick volume in Planck units. Volume in Planck units is a very suspect thing. You measure area in Planck units. The area in Planck units is a natural thing, but still, I can't really support strongly everything I've said. What is this? I don't even remember what this is. Oh, this was redoing, yeah. All right, so let me just remind you then, for the various possibilities, the scale factor, the light cone time measure, and the information measure gave very similar formulas for the measure. All of them had the same e to the minus 3 ht naught, and they basically differed by prefactors. There are additional prefactors here that really do come into it. Ben talked about them a little bit. But they do differ in the direction that as you go from scale factor to information, it goes from 1 to 1 over h cubed to 1 over h. The light cone time, which is what Ben talked about, is rather singular at low h. And that's what led to the prediction that the cosmological constant would be determined by the size of the landscape, that it would be the smallest cosmological constant that you could find in the landscape, or at least the smallest cosmological constant consistent with what you're looking for, namely observations. And that came from this 1 over h cubed here. The 1 over h coming from the information is a much softer thing, and it would not have this property. It would simply say that this nice distribution here is what determines the probabilities for H, not the endpoint of the distribution. And so, you know, it would say the probability is peaked in the vicinity of somewheres where H times T naught is of order 1. So it wouldn't be an accident of the number of vacua in the landscape. It would just be a consequence of the simple formula. Okay, I think that's what I wanted to tell you about. And it's a game. At the moment, I can't confirm a lot of it. Hopefully next year, my clever students will have sorted it all out and have rigorous proofs of it. Thank you. John. Oh, I'm not good at empirical questions. Absolutely. Well, yeah, we are entertaining that, but no, we are not entertaining that. We're not entertaining that. We're simply finding a mapping that conserves probabilities. At no point do I ever want to say that somebody outside a horizon can detect what happened inside the horizon. There's no way to confirm it. It doesn't mean anything. I simply want to say there's a mathematical correspondence between the two that's gotten by unitary conjugation. And that's the way I would prefer to leave it. I would not like to say that we can see anything happening, you know, literally. I don't want to take that literally. The mathematics tends to suggest that there's a mapping of observables. That's all. That's as far as I would go. Yeah. You know, I don't know. In principle, I would think so. And I don't know the answer. Good. Or hats, or other hats. Yeah, good, right. That's one of the things that, look, let me tell you how I do things. Joe knows this. He knows that I come for the conferences in order to get myself into a terrible state of panic in order to try to figure out some story to tell you guys. My panic really erupted about a week ago, and so I put the story together. Now, I didn't get that far. Okay, good. No. Yes or no? Yes or no? The goal of it, for me, was to find a rationale for why there should be a specific measure, and then to try to use some arguments to see which of the several interesting measures. Once you do this, the hell with the census taker. The hell with the census taker. We now have a set of rules that are for the approximate but useful world of the effective description inside the multiverse. I regard it as an information problem, a general information problem to derive a measure, and my feeling is you have to get the information aspects right if you want to be really. If you want to know what you're doing. So that's why I'm doing this. At the end of the day, we're not going to ask the census taker to decode the Hawking radiation. That's not the way we're going to figure stuff out. We're just going to go back behind the horizon and use low-energy physics. But are now armed with some argument for a cutoff. Yeah, with the conservation of information, that sort of thing. Now, as I said, I'm very squeamish about this because the number of guesses that I've made probably exceeds the mean free path of an error, but yeah. Oh yes. Yeah. But yes. We want to ask how much we can. Absolutely. Well, for the same reason that Alan does. I mean, and the same reason all inflationary people do. They would like to know how much they can. You hope that there's an attractor. You know, having an attractor is a good thing and a bad thing. It's a good thing in that perhaps you don't have to know all that much about the initial conditions. It's a bad thing because you don't find out about the initial conditions, right? So, so that's all. It's nothing fancy. Just right.
So I'm trying to understand this idea of cutoff. Is this something that you think is fundamental to the theory, or there will be hopefully something more fundamental that will?
Well, you know, is the idea of a cutoff fundamental for a quantum field theory?
Well, exactly.
Yeah, I think so. Quantum field theories, everything's infinite if you don't cut them off.
It's fundamental to do calculations, but you always think that there is some more fundamental theory that replaces the cutoff.
Yeah. A more fundamental theory that would replace the cutoff or that would provide a cutoff would be a theory of the end of time. If there is an end of time, then you have a cutoff, period.
That's certainly one way to think about it. If universe is an lattice, that could be a way to cut off one. But that's not the only way to do something about it. For example, for point interaction, you could have electroweak,
Right.
which is more complete.
It's a very interesting question that I don't know the answer to. Whether they're very sure. I mean, yeah, one does hope that there's a more complete description. Sure, of course.
But Alan will think that he cannot think of this as an end of time, limiting off to infinity, right? And that there's a really real difference between the infinite time he needs and that kind of limit. So that's really
Alan believes in the end of time or doesn't?
He believes absolutely not in the end of time.
Good.
Okay. So
I was being
facetious.
I was trying to pull his chain.
Okay. Well, that's
I didn't get a laugh out of it.
consistent answer. That's a consistent answer, right? So there might be sense.
So we're following trajectory bundles.
Yeah.
And you have an information quantity that you can observe. It turns out that at least the scaling for that quantity is exactly what we get from the principal function in inflation. HAQ is what it is, but it's basically the derivative of HAQ of the action, which is telling us, I think, that what we are trying to do.
About it
Yeah. Except that there's another way of potentially interpreting it, which is that it's space. Space.
what?
Well, phase in the sense that the principal function is actually encoding phase. ds equals 0 is the phase thing in Hamilton Jacobi dynamics. Right? So the interesting thing is when Saltek and I fooled around with this stuff, we had no, it's not. But what we got was the Hamilton principal function, which is HAQ, and we divided by HQ because we wanted to make it Bernoulli. We called that the reduced action, and we used that as the basis of using log h for h of phi as the sort of way to look at inflation, which worked very well.
Fortunately, I'm coming to Toronto speaking a little about them.
But it is sort of interesting that, in fact, it does seem like there's going to be a relationship between that. Because basically what we're doing is we're doing essentially a pretty classical flow of information. Right? I mean, it's not like you're bringing new stuff
investigate what does a typical or the majority of observers see, and the answer from this point of view is that the typical observer sees a Hubble constant which is inverse with his I mean, not my, not that. Yeah, that's the